Welcome back. Today we will discuss the flow through pipes. Flow through pipes is one of the most common applications in industry. Almost all process industries, that include chemical industries, pharmaceutical industries, involve some reactors in which fluids are moving in and moving out. The fluids are supplied through pipes. So we need to worry about the pumping power required. The first reported experiments connected with the flow of pipes are due to Reynolds that we have discussed earlier. Reynolds, a British scientist, conducted experiments on a glass tube submerged in water through which the fluid, that is water, flowed through and the rate of flow was controlled by a valve. To study the behavior of the fluid, Reynolds injected a dye at the center of the tube. The dye came on as a streak and he studied how that streak behaved as the time passed on. These are the sketches from the first paper of Reynolds. He found out that when the speed of flow was low, the streak appeared as a smooth filament and went down the tube. As the flow speed increased, the streak started diffusing outwards, and for larger speed, the streak became turbulent. So he concluded that low speeds, the flow through a pipe is laminar and is turbulent at high speeds. These are some recent pictures of the flow through the same equipment. Here, this first picture is at a low speed. Then, as the speed increased, the streak of dye started changing character, and by this speed, there was no longer a smooth streak, but largely dispersed dye. This transition from laminar to turbulent is interesting. While laminar flows are dominated by viscous forces, turbulent flows are dominated by inertial forces associated with large-scale mixing of the fluid. It stands to reason that in geometrically similar situations, the transition from laminar to turbulent flow should occur at a fixed ratio of inertial and viscous forces. Since the Reynolds number measures this ratio, the transition should be marked by a fixed value of the Reynolds number, which is defined as rho V average d, the diameter of the tube, divided by the viscosity of the liquid. The value of Reynolds number at which the transition from laminar to turbulent flow takes place is called the critical Reynolds number, RECR. When the Reynolds number is below 2300, the flow is always laminar, and any disturbances in the flow is quickly dammed out. However, when Reynolds number is increased, the flow may or may not be turbulent depending on the conditions at the inlet and the levels of vibration in the experimental setup. Johannsen and Lowe did the experiment in 1983 on the same equipment as Reynolds used in his laboratory at the University of Manchester. Reynolds had reported that the transition took place at Reynolds number as high as 100,000. But in the later experiment, a century later, they could never take the transition beyond about 8,000. And that was largely because the roads near the laboratory in University of Manchester are now busy roads with a lot of traffic. The traffic causes disturbance in the building, and because of the vibrational environment around the laboratory, the transition now takes place earlier. If great care is taken in making the pipe walls very smooth and in suppressing the turbulence in the incoming fluid and in isolating the experimental setup from external vibrations, the transition can be delayed to as high a Reynolds number as 100,000. But for most engineering applications, a value of 2,300 represents a good choice for the critical Reynolds number. We had earlier discussed the flow at the entrance of a pipe. When the flow enters a pipe with uniform velocity across a section, soon the viscous action at the wall takes over and slows the fluid down at the wall. So the flat velocity profile at the entrance changes into velocity profile where the velocity is 0 at the wall by no slip condition, but the velocity is uniform in the center. As the flow proceeds down the tube, more and more of the flow area is affected by the viscosity till at this location all of the area is now affected by viscosity. Beyond that, the profile does not change. This is the region over which we say that the flow is developing. And beyond this is what is termed as the fully developed flow. How long is the developing flow region? Again, this region should depend upon the inertial and the viscous forces. So, this should depend only on the Reynolds number. The length over which the flow is developing is termed as the entrance length, and it increases with the Reynolds number. One commonly used correlation for entrance length for laminar flows is LE is equal to 0.06 Reynolds number based on the diameter of the pipe or the tube. While in the turbulent flows, this correlation is LE is equal to 4.4 into RED raised to power 1/6. The entrance length in turbulent flows is much smaller than those in laminar flows. Consider, for example, a flow at Reynolds number 2,400. In this value, the flow could be laminar as well as turbulent depending upon other conditions. If the flow is laminar, Reynolds number is 2,400, so the entrance length is 0.006 times the Reynolds number, which gives us 144 diameters. But if the flow is turbulent, this entrance length is only 16 diameter. Thus, the entrance effect is negligible more often in turbulent flows than in laminar flows. But as you remember, most commercial flows are turbulent, so the entrance effect can be neglected in many situations. This illustrates the difference in the profile through a laminar flow and in a turbulent flow. The flow profile in laminar flows is parabolic with mean velocity 1/2 of the maximum velocity, while the velocity profile in turbulent flows is quite flat at the center. It is much sharper at the walls, and because of this, there are larger shear stresses on the wall than in the case of laminar flows. And because of this, there are much larger pressure drops. Much shorter developing lengths, as we discussed, and then we know the most flows are turbulent. Water flowing in a 10 centimeter diameter tube at a speed 20 centimeters per second is likely to be turbulent. A few lectures ago, we obtained the laminar velocity profile for fully developed flow in a pipe. We considered an annular control volume. In this element, we wrote the forces, the pressure forces and the shear forces. Because of full development, these two forces should be balancing. There should be no net force, and the force balance gave us this relation for W, the velocity component in the z direction. We showed that P prime is constant, that is, there is a linear pressure gradient down the pipe. From this, we obtained the velocity profile, and the velocity profile is parabolic in R. Capital R is the radius of the tube, this velocity profile, and on integrating this, we found out the flow, and then from the flow, we found out the average velocity, which was minus P prime R square by 8 mu. The volume flow rate was determined as pi r raised to the power 4 divided by 8 mu into minus P prime. This is known as Hagen-Poiseuille law and depends upon two conditions. The flow is laminar and it is fully developed, that the length of the pipe is much larger than the entrance length, so that the entrance length, the end effect, can be neglected. This is for laminar flows, but laminar flows are few. So we need pressure drop relations for turbulent flows. Since the analytical solution for this problem is not available, we resort to experimentally develop correlations for the purpose. Since the pressure drop depends on several parameters, namely the density and viscosity among the fluid properties and the length, diameter and the roughness of the pipe wall, we need to develop pi numbers to reduce the number of independent parameters in the problem, using the techniques that we learned in last few lectures. So, what is our problem now? Given a pipe of length L and diameter D, find out the total pressure drop in the pipe when the fluid of density rho and viscosity mu flows through this at a given volume flow rate. There are two forces that are important, the pressure forces and the viscous forces. And in addition, we write the inertial forces. So we develop the scale factor for all of these three types of forces and equate them. Since there should be only one force vector, and from this we obtain two pi numbers. We have Kfi for the inertial force, which should be Km times Ka, where m is the mass and a is acceleration. Mass is like rho times volume. So K mass is K rho times KL cube, and Ka, as we have done a number of times earlier, is Kv square by Kl. So this gives us Kfi is equal to K rho Kv square Kl square. And from this we get a pi number. F inertial force divided by rho v square L square. Similarly, we develop the pi number for the viscous force, and pi number for the viscous force is obtained as F mu, the viscous force, divided by mu v L, the same pi number that we obtained in the last class. The third pi number we deal with is the pressure force, which is pressure into area. For pressure, or rather pressure difference, we have K delta P, and for area we have KL square. And so Kf for the pressure force is K delta P times KL square, or pi is equal to Fp divided by delta P L square. Notice that we have converted P into script P, which is the non-gravitational pressure discussed earlier. These three scale factors must be equal. From these we get two pi numbers. The Reynolds number rho VL by mu. It is assumed that all values are characteristic. The Euler number delta P divided by 1/2 rho V square. 1/2 is there because of convention. This assumes geometric similarity between the flows. The length L of the pipe and its diameter d are the obvious geometrical parameters. In addition, a French engineer by the name M. Darcy showed experimentally in 1857 that the pressure drop in turbulent flows is also affected by the roughness of the pipe wall. The wall roughness may be characterized by the mean height epsilon of the roughness elements on the wall. And therefore, the non-dimensional geometric parameters are L by LC. LC is the characteristic length. L is the length of pipe. So L, D, and epsilon are the three geometric parameters. So we get three non-dimensional geometric parameters: L by LC, D by LC, and epsilon by LC. We still have to choose what LC we use. We can then write any non-dimensional dependent parameters like pressure drop as a function of Reynolds number, Euler number, and these geometric parameters. The most common problems encountered in pipe flows is to evaluate the piezometric pressure drop delta P for a given flow rate. The non-dimensional piezometric pressure drop is delta P divided by delta P characteristic, can then be written as a function of Reynolds number, Euler number, L by LC, D by LC, and epsilon by LC. It is convenient to use diameter of the pipe as the characteristic length in these problems. And we use the average velocity of the fluid through the pipe as the characteristic velocity. There is no characteristic difference in the pressure in the independent parameters, and so we can choose it arbitrarily. If we choose the characteristic pressure difference delta P as 1/2 rho V average square, the value of delta P divided by 1/2 rho V square is rendered as unity, a constant, and so it drops out from the functional relationship. If we treat delta P as dependent parameter, then the functional relation becomes delta P divided by 1/2 rho V average square is a function of Reynolds number L by D and epsilon by D. We can find the pi numbers by dimensional analysis also. The dimensional analysis was introduced in the last lecture. We start with the list of parameters. The basic group, as we defined there, are rho d V average. The independent parameters which contain all the dimensions involved. There are 3 dimensions involved, M, L, and T here, and so we choose 3 independent parameters as the basic group, and rho d V average involve all these 3 dimensions and do not form any non-dimensional parameter amongst themselves. The other independent parameter which are not in the basic group are mu, viscosity, length L of the pipe, and epsilon, the mean roughness height. And we write one dependent parameter. In this case, it is delta P, the piezometric pressure drop. We write the dimensions of all these parameters. So then we formed for other parameters and variables, that is this group. We take one of these and multiply them by rho raised to power A, L raised to power B, and V average raised to power C. And then determine the values A, B, and C, which will make this non-dimensional. If we use viscosity, we get a parameter mu divided by rho V average D as non-dimensional pi number. The inverse of this is the Reynolds number. With L, you get L by D as a non-dimensional parameter. With epsilon, you get epsilon by D as a non-dimensional parameter. With delta P, the dependent parameter, we get delta P divided by rho average V square as the dependent non-dimensional parameter, pi 4. So we can write the equation just like before. Delta P over 1/2 rho V average square is a function of Reynolds number L by D and epsilon by D. Now, if the pipe is very long compared to the entrance length LE, we may assume that the flow is fully developed along the entire length of the pipe. Then the pressure gradient is constant in the pipe. If pressure gradient is constant in the pipe, then delta P should increase linearly with L. And so we can write delta P 1/2 rho V average square is L by D. The length parameter non-dimensional is taken out. Linear, delta P is linear with L, so it can be written as L by D times a function of Reynolds number and epsilon by D. The dimensionless function of Reynolds number and epsilon by D is termed as the Darcy friction factor and is denoted by F, lowercase f. So in terms of F, The pressure gradient parameter delta P divided by 1/2 rho V average square is simply F into L by D. Or in terms of the head loss, we can write head loss HL is, which is delta P by rho G, is nothing but F times V average square divided by 2G into L by D. For laminar flow region, we know V average is minus P prime R square by 8 mu. And if we cast this in the form of F, we get F is equal to 64 by Re. So in the laminar flow region, the friction factor, the Darcy friction factor F, varies like 64 by Re. Many researchers at the beginning of the 20th century did extensive work on determining the dependence of F on Reynolds number and epsilon by D. The prominent among them were Nicorazzi, who worked with pipe walls roughed with sand grains of different sizes, Hunter Rouse, a very famous fluid dynamicist, R.J.S. Piggott. Rouse and Piggott worked on developing a representation chart of the data. Colebrook, who experimentally developed a correlation of the friction factor with the Reynolds number and epsilon by D, and Louis Moody, who is credited with putting the work of all these people together into a chart which is famously known as Moody chart or Moody diagram. This is what a Moody chart looks like. Moody charts helps us determine the friction factor F, the Darcy friction factor, as a function of a Reynolds number with the relative pipe roughness parameter epsilon by D as a parameter. Thus, given a Reynolds number and given a roughness parameter epsilon by D, we can locate a point on this chart and read from the left-hand scale the effective friction factor. You would notice a few things. On the left-hand side, laminar flow is a straight line represented by 64 Re. Since it is a log-log plot, a relation F is equal to 64 by Re would plot as a straight line. This is for laminar flow up to a Reynolds number of about 2000. Then this gray area to something like 3000 is an area which is the transition region, and one is not very sure of what the friction factor is in this region. After that, there is turbulent region, and the turbulent region is divided into two portions by this broken line. On the right of the broken line, the flow is called fully turbulent, and you notice that in this region, the value of F is quite independent of the Reynolds number. It depends only on epsilon by D. We'll exploit this fact in solving the problems. To the left of this, the flow is not fully turbulent, and the friction factor depends both on Reynolds number and epsilon by D. This limiting line is for epsilon by d 0, that is for a smooth pipe. Colebrook developed a formula for Reynolds number greater than 4000 and which is widely used in computer calculation. 1 over root f is equal to minus log of epsilon by d divided by 3.7 plus 2.51 divided by Reynolds number based on diameter times root f. There are various online calculators available. One of these calculators is at this address. If you Google search a Colebrook formula calculator, you will get a number of calculators there. For smooth pipes, the line which was the lowest, the friction factor is given by F is equal to 0.184 divided by Reynolds number raised to power 0.t. This is valid for the range of Reynolds number between 5 into 10 to the power 5 to 5 into 10 to the power 6.